In this video, we are going to see what happens when we have rates that are related to each other. For example, in this case, we are given a curve 2x to the power 3 plus 3y squared equal 19. And we know that an object is moving along this curve. And the question is, when y equals 1, if we know that the rate of change of y in t, okay, the rate at which the second coordinate changes is -2, what is going to be the rate at which the horizontal coordinate is changing? So here's something that helps is to have a visual of what's happening. So I went ahead and did a plot of the curve. Okay, you see that this curve, of course, cannot be, this is not a function because it doesn't pass the horizontal line test, right? But that's the reason why we are given a curve in implicit form, okay? All right, so it's saying when y equals 1, so here we can, y equals 1 would be this point here, right? And we have here two rates of change. One is the rate of changing the coordinate y, and the other one is the rate of change in the coordinate x. Okay, and we know dy dt, so the question the problem is asking is find dx dt. So let's get to it. Now the curve we are given, let me copy paste. Here the information we have is dy dt. Okay, we know that it's equal to -2. And we also have that this happens when y equals 1. We need to use that. So we need to find dx dt. Why am I insisting on this? Because we can use implicit differentiation, okay? X and y are implicit functions of t. Think about it. As the object is tracing the curve, for every time it will have a pair of coordinates x and y. So both coordinates x, y are a function of t. But because we know that it's tracing this curve, the curve itself is defining implicitly the coordinates x and y as functions of time. So we can just differentiate implicitly. Okay, it's basically the same idea we have been doing with a little twist. So we differentiate both sides with respect to t. And now we have 2 times 3 times x squared. But now because x is a function of t, I need to write dx dt plus 3 times 2 times y times, remember, y is a function of t, so dy dt equal 0. Now, because it's equal to 0 and it's multiplied by 6, both of them, I can just get rid of them and I get this relation. X squared dx dt plus y dy dt equal 0. So this is a relation between the two derivatives that we need to work with, okay? Remember, dy dt we have, okay? Y equal 1 we have. And then when we look at the other side, x squared we don't have, and dx dt we need to find. Okay, so the goal here, first thing we need to do is to find x. How do we find that? Well, we know that it's a point of the curve, and we know that y must be equal to 1. So that means 2x to the power 3 plus 3 times 1 equals 19. That means 2x to the power 3 equals 19 minus 3, which is 16. That means x to the power 3 is 8. That means x must be equal to 2. Let's check on the picture. And it looks like this is correct. You see, because here this is 2. And it looks like the coordinates of the point are 2, 1. Okay, so that looks good. You can do this problem without plotting the function, but since we already did, it's good to have a visual of what we are doing. All right, so going back to this relation that we found, we have that 2 squared times dx dt plus y equal 1 times dy dt, which we said was negative 2. Here we have it, right? Times negative 2, and this must be equal to 0. So we are set. So this is dx dt equals 2 divided by 2 squared. So that's 1/2. So the final result is dx dt equals 1/2.